Hello, welcome back. Today we are going to start with module 5, that is module 5, that is limit state design of columns and footings. So this has two parts, that is columns and footings. So to start with, let us cover design of columns, that is limit state design of columns. So as you all know, column is an element in the structure, or it is a structural element. Okay, a structure consists of several elements like beams, columns, slabs, etc. So column is very important because if slab fails or if a beam fails, then it is going to be a local failure. If a column fails, then it is possible the whole structure may collapse. Okay? So we'll have to be careful when we are designing a column. Column is very, very important. So what column does is, it is going to take the load from the beam. In turn, the beam takes the load from the roof. Okay? Roof carries live load, dead load, partition walls, etc. So that is going to be transferred to the beams. Then the beams will transfer finally loads to the column, then to the footing, then to the soil. So in case of course, flat slab, flat slabs themselves transfer load to the column directly, not through the beams. So it is out of the syllabus for you. We shall not worry about flat slab and other things. We only worry about the slab, beams, then the columns. Okay? So what is a column? Column is a compression member. It carries load by compression. So when a column is subjected to axial load, it is not going to be subjected to axial load alone. It is going to be subjected to moment as well. Okay? So here in this case, an RCC column normally will be of rectangle, circular or square. Of course, depending on the architectural requirements, you can change the shapes of the columns required, like hexagonal, L-shaped columns, etc. But we are not going to cover those parts. Okay, we are going to cover only rectangular, square and circular columns here. So as I said, column takes compression. If we use concrete, because concrete is good in compression, weak in tension, then we can say, okay, just by putting concrete, we can construct a column. No, it is not so. Because there are different reasons why we use reinforcement in the column. So by using reinforcement in the column, what we can do is, we can reduce the dimensions of the column for a given load. Okay, not only that, a column will not be subjected to, okay, almost always axial load is accompanied by some magnitude of moment. So when a column is subjected to some moment, it is possible one of the faces of the column may be subjected to tension. Okay, to take care of that part, what we do is, we are going to provide reinforcements in the column. Okay, so column reinforcement serves the purpose of taking care of accidental moment, and normally it is going to be subjected to, as I said, both axial load and moment. Okay, and also it helps in reducing the column size. Is it clear to you? So when we use these reinforcements in a column, and when we put concrete, and it is possible the column may buckle. Say if this is the plan and this is the elevation, okay, reinforcements we are providing to the column. These are the vertical reinforcements. So imagine for a moment you are not providing any lateral ties. So when you apply load to the column, of course reinforcement and the concrete are going to share certain magnitude of the load. Okay. So it is possible because the the reinforcement is slender, the reinforcement may buckle out. Okay, that may result in the failure of the column. So for that purpose, what we do is we are going to provide the reinforcement in the horizontal direction, and these reinforcements are called lateral ties or lateral reinforcement. So that is, it looks this way in the plan. Okay. So this is lateral reinforcement. Lateral reinforcement. These are main reinforcements, or these are longitudinal reinforcement. These are longitudinal reinforcements. Of course, the code says whenever you are designing a column, so how much reinforcement you need to provide. So what is the minimum area of reinforcement and what is the maximum area of the main reinforcement you need to provide, and also what are the diameters of the lateral ties you need to fix, and what are the spacings of those lateral ties we need to provide. And all those things are going to be covered in this module, okay, and as per the Codal recommendation. So here I have shown the 4 bars. This is a rectangular or a square column. So we need at least 4 bars or 4 main bars or 4 longitudinal bars. If we need additional, of course, we can provide additional reinforcements here. Okay, if it is a rectangular beam, if you need additional reinforcement on this face, at certain spacings, we can provide additional reinforcements. Is it clear to you? Then coming back to the classification of columns. See, what the code says is, if the column effective length to the least lateral dimension, least lateral dimension is less than equal to 3, then that compression member is considered as pedestal. Okay. If this value is greater than 3, then it is a column. It's a column. So when it comes to column, there are 2 types. One is a short column and the other is a long column. So what is a short column and what is a long column? If effective length of the column divided by the dimension D or B, that depends on which, B or D, about which axis we take, then we take accordingly B or D. Okay. If LEFF divided by B or D is less than 12, then it is a short column. It is a short column. Okay. If this is greater than equal to 12, then it is a long column. Okay. So here in your syllabus, we don't deal with long columns. We only concentrate on the design of short columns. Okay. Not even pedestals. Only short columns. Okay. So there are some more codal provisions or codal recommendations we need to take care while designing. So right now what I am going to do is, please write down the notes. I am going to give you the notes. Please write down, okay, and it is very important, and certain things, certain theory part is going to appear in the examination. So please write down that part. Okay. So write columns. Write this module 5, limited design of columns and footings. So columns, write down a column is a very important element of a structure. Full stop. Columns support beams which in turn support walls and slabs. Full stop. The failure of a column results in the collapse of the structure. The collapse of the structure. Full stop. Next line. Column or strut. Column or strut. S-T-R-U-T. Or strut is a compression member, comma, the effective length of which exceeds 3 times the least lateral dimension. Excuse me. The least lateral dimension. Within brackets, you write 25.1.1, page 41. Page 41. See, when I say least lateral dimension, so I said a column may be a rectangular shape, may be of rectangular shape, or a square, or a circle. In case of rectangular section, so we have 2 different dimensions. One is width and the other is the depth. And this width is less than the depth. That means, which is the least lateral dimension out of these 2? Smaller one. That is the breadth of the column. Smaller dimension is the least lateral dimension of a column. Is it clear to you? If we take a square column, if it is of square shape, same dimensions all over. So whatever the dimension, that is the size of the square itself, is the least lateral dimension. If you take a circular column, so diameter, it is a constant value. So least lateral dimension is the diameter. Is it clear to you? So next paragraph. When a member carrying mainly axial load is vertical, comma, it is termed as column. It is termed as column, comma, while if it is inclined or horizontal, comma, it is termed as strut. It is termed as strut, full stop. So what it means is, if the member is vertical like this, it's a compression member vertical, this is a column. If a member is inclined or horizontal, this is called as strut. Okay? Full stop. Next paragraph. Compression member whose length does not exceed 3 times its least lateral dimension is called a pedestal. Is called a pedestal. Underline it. So within brackets you write under note. Under note, page 49. If you go to page 49, in the first column on the top there is a note. So that says about the pedestal. Full stop. Next line. An RC column, concrete, an RC column concrete has a high compressive strength and a low tensile strength. Full stop. Hence, comma, theoretically, comma, concrete should need no reinforcement when it is subjected to compression. When it is subjected to compression. Full stop. Reinforcements are provided in order to reduce the size of columns. Full stop. Though a column is mainly a compression member, comma, it is liable, L-I-A-B-L-E, liable, L-I-A-B-L-E, liable to some moment due to due to eccentricity of loads, due to eccentricity of loads, full stop. So, it is necessary to provide reinforcement near all faces of the column, full stop. These reinforcements form FORM, the longitudinal reinforcement. Within brackets you can write steel, that is longitudinal steel. Put a full stop. Longitudinal reinforcing bars are tied laterally TIED, laterally, LATERALLY, by ties, TIES. These are lateral ties. Okay, by ties at suitable interval, so that bars do not buckle. Full stop. So what I mean is, as I explained already, just imagine for a moment you don't have any lateral ties or lateral reinforcement. So if you construct a column just using all those vertical bars or longitudinal bars, so when it is subjected to load, so the main bar or the vertical bar is likely to buckle outwards, sideways. Okay? So to avoid that, what we do is we are going to tie them together, okay, by putting reinforcement all around the main reinforcements. So these reinforcements are called lateral ties. This is the plan I am seeing. This is the elevation. Okay, and these lateral ties are spaced at certain distance as recommended in the code. Okay, even the diameter of the lateral ties we are going to select depends on the codal provision or the codal recommendation. Okay, so when we put lateral ties, not only the lateral ties keep all the main reinforcements in their position, in their respective positions, it avoids buckling of the main reinforcement. Is it clear to you? And again, the spacings as specified in the code book, the reason is even the main reinforcement tied laterally using lateral ties, in between those lateral ties, the main reinforcement, a part of the main reinforcement column acts as a column. So if the spacing is too much, then this may buckle sideways. To ensure the reinforcement does not buckle in between those two lateral ties, we have to maintain certain minimum spacing. Okay? Not certain minimum spacing, certain maximum spacing. Full stop. Continue. Lateral ties also maintain the position of the longitudinal reinforcements. Full stop. Lateral ties are also called as transverse reinforcement. So, lateral reinforcement or transverse reinforcement. Transverse So, I am going to write this as lateral reinforcement or lateral ties. Okay. This is also called as transverse reinforcement. Okay, full stop. Next side heading is classification of columns. Classification of columns. Depending on the slenderness ratio, comma, a column may be a short or a long column. Full stop. The slenderness ratio of a column is the ratio of the effective length of the column to its lateral dimension, full stop. Next line, a column whose slenderness ratio less than 12 is called a short column, and if it is greater than equal to 12 is called a long, within brackets you write slender column, full stop. Write 25.1.2, page 41 of the code book. Page 41 of the code book. Next, assumptions in limit state of collapse in axial compression. Collapse in axial compression. Okay. So for that you refer 39.1, page 70. Page 70. And the next is functions of longitudinal and transverse reinforcements in a column. Functions of longitudinal and transverse reinforcements in a column. Point number 1, that is A. Longitudinal reinforcement. Longitudinal reinforcements. Under that you write point number 1. Write point number 1, longitudinal reinforcements. Under that, point number 1, to share the vertical compressive load, comma, thereby reducing the overall size of the column, the overall size of the column. Next, point number 2. Point number 2, to resist tensile stresses caused in the column due to eccentric load, comma, moment and or transverse load. Moment or transverse load. Next, point number 3. To prevent sudden brittle failure of the column. To prevent sudden brittle failure of the column. Point number 4. Point number 4. To impart IMPART, to impart certain ductility to the column. Next, point number 5. To reduce the effects of creep and shrinkage due to sustained loading. Due to sustained loading. Full stop. Next, B, transverse reinforcements. Transverse reinforcements. Underline it. Point number 1. To prevent buckling of longitudinal reinforcement, point number 2, to resist diagonal tension, to resist diagonal tension caused due to transverse shear, due to moment or transverse moment or transverse load. Moment or transverse load. Next, point number 3. To hold, 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 the longitudinal reinforcement in position at the time of concreting. At the time of concreting. Next point. Next point. To confine the concrete, comma, thereby preventing its longitudinal splitting. Longitudinal splitting, SPLITTING. Next point, point number 5. To impart ductility to the column. Next, point number 6. To prevent sudden brittle failure of the column. Full stop. General design consideration for a column. general design consideration for a column. So please write down this figure. This is the floor level. This is slab. This is main beam. So this is, I will write slab thickness. Slab thickness. So this is the column. And this is the secondary beam. Secondary beam. So if you look from the top at this level for the column, you will see this figure. Okay, and this is y-axis, this is x-axis, and this dimension of the column is greater than the dimension perpendicular to this. So this is the unsupported length of the column measured when the column is bending about its major axis xx. This is unsupported length Ly when the column is bending about its minor axis. So how do we measure the unsupported length? Unsupported length is measured from the floor level to the bottom of the beam. Because we have beams running in both directions. So this is the column and this column is supporting beam in this direction as well as beams are running perpendicular to the board. So these are secondary beams. Is it clear to you? So as a result, this column is likely to bend in both directions. That is in both axes, both xx axis and yy axis. Okay? So when we take the xx axis, so this is the beam that is preventing the column from bending about the xx axis. That is this one, the bigger column, sorry, the bigger beam. Okay? So you must measure from the floor level to the bottom of the beam as the unsupported length of the column about XX axis. I call that as LX. Similarly, because we have beams perpendicular to the board, so it may even buckle about YY axis due to the presence of these beams. Okay? So the distance measured from the floor level to the bottom of the secondary beam is the unsupported length when we consider the bending about YY axis. Is it clear to you? So going further, write down short, and long. Another name for long is slender compression members or columns. So write down. And one more thing I forgot to write. If this is the width B, this is the depth capital D. Basically, this is the shorter dimension and this is the longer dimension. Write down. A compression member is considered as short when both the slenderness ratios, slenderness ratios LEX divided by D or LEY divided by B or less than 12. That is 25.1.2, page 41. 25.1.2, page 41, where LEX equal to effective length with respect to the major axis. LEY equal to effective length with respect to the minor axis, and D equal to depth with respect to the major axis, and B equal to again depth with respect to the minor axis. Is this over? Next, unsupported length So refer figure shown here. So this is the figure I am talking about. Okay? This is the unsupported length. Unsupported length with respect to the major axis, and this is the unsupported length with respect to the minor axis. So refer figure shown here and also 25.1.3b, page 42 of the code book. Page 42 of the code book. Full stop. Next is slenderness limits for columns. Write down. Write down. The unsupported length between end restraints shall not exceed 60 times the least lateral dimension of a column. Within brackets, you write 25.3.1, page 42. Page 42. 3.2, I mean. Page 42, where B equal to breadth of the cross section and D equal to depth of the cross section measured in the plane under consideration. Full stop. Minimum eccentricity this is as per 25.4, page 42 of the code book. So minimum eccentricity should be L divided by 500 plus DRB divided by 30 and not less than 20 mm. Okay? Where L equal to unsupported length. This may be about the x-axis or about the y-axis. So, depending on whether you take Lx or Ly here, you take D or B. Okay. So, whenever we design a column, we have to design the column for at least some minimum eccentricity. So, what is that minimum eccentricity value? So, minimum eccentricity value is this one. Find out what is the eccentricity by taking the unsupported length L, Lx or Ly. If it is Lx, depth. If it is Ly, take B and find out what is the value. And whatever the value we get should not be less than 20 millimeter. Say for example, if this is say 17 millimeter, then we have to design the column to take care of at least 20 millimeter minimum eccentricity. What in case this value equal to 24 millimeter? Then you take 24 millimeter in general. So, find out this value, take higher of these two values as the minimum eccentricity. Is it clear to you? Hello, and the next point is reinforcement requirements. Okay. That is longitudinal reinforcement. That is 26.5.3.1, page 48. So, point number A, please write down point A, minimum area required equal to 0.8% gross area. Maximum area required equal to 6% of gross area. That means if you are designing a column, if the reinforcement, that is the area of steel you need, is less than 0.8%, then what you have to do is you have to provide at least 0.8% of the gross area of reinforcement. And the maximum reinforcement is 6%. The reason we are restricting the steel area to 6% because when you put 6% steel, even 6%, if you put concrete, it is really hard to compact concrete because 6% steel is too much. Okay, that is the main reason. So again, when you are designing a column, first you are going to fix up the dimensions of the column, then you are going to find out what is the area of steel required. If the area of steel required is greater than 6% of the cross sectional area. In such cases, what you do is, whatever initial dimensions you assume or you took for the column is not adequate, go ahead and increase the dimensions of the column. That's what it means. Next, point B, I don't think you need point B now, so you don't have to worry about it because it needs a little bit of explanation. So I am not going to worry about that. Next, point C, minimum number of bars, that is minimum number of bars, minimum number of bars, that is 4 for a rectangular section, 6 for a circular section. So rectangular or square section. Okay. So what it means is, if you have a rectangular column of certain dimensions B, D, overall depth, so the minimum number of bars you need is 4. Okay. And according to the design, if you need more bars, of course you can provide bars here, on this side and on this side. If you take a rectangular section, so minimum number of bars you need to provide is 6 minimum. Of course you can provide more. Okay. So that is for a circular section. This is rectangular section or square section. This is a circular section. Is it clear? So we will go with the next point, that is point D. So minimum diameter of bar, write down, or else just write down that figure. Next, point number D. Minimum diameter of bar, minimum diameter of bar is 12 mm. Of course, we have bars starting from 6 mm, 8 mm, 10 mm, 12 mm. So especially for a column, so the minimum diameter of the bar should be 12 mm. You should not use 10 mm dia bars for columns. Okay, 12 and above. And the next point is E. So it says any column with helical reinforcement should have at least 6 bars. So what it means is, I am not going to write down that point, I am going to briefly explain what it is. So we have 4 bars, we are going to provide lateral ties or lateral reinforcement like this. Similarly for this, Yes, of course we are going to provide lateral ties and whose shape is circular. Okay. So in case of helical reinforcement, see here we are providing rings, circular rings at certain spacing. Here also we are providing rectangular links at certain spacings. Okay. So if you provide helical reinforcement, what is the meaning of helical reinforcement? It is like, these are the lateral ties, single bar, it is wound around like this. If, say for example, if this is the circular column, okay, these are the main reinforcements. Okay, normally we are going to provide lateral ties like this, and also we can provide circular reinforcement, that is like this. Same reinforcement, lateral reinforcement, and same means it is a single wire, it is wound around the column. That can be done for circular as well as for a rectangular section. So in such cases, what the code says is, even if it is rectangle, if you are providing a helical reinforcement, that is the reinforcement going around the column, then we have to provide at least 6 bars. Is it clear to you? Next point, point G, spacing of bars measured along the periphery of the column, shall not exceed (300 millimeter). So what it means is, say for example, let us take this. Let me assume this dimension d, that is the overall depth of this column to be say around 750 millimeter. Okay, or and with cover, say I am going to give 60 mm cover, say 50 mm cover, side cover. Here also 50 mm cover. Okay, 750. So 50 mm this way, 50 mm this way, I am left with this spacing of 650 mm. Okay. So in this case, what is the spacing between these two bars? It is 650 millimeter. But the code says, so the spacing should not exceed 300 millimeter. This is the periphery of the column. So in this case what we do is, say let me put one bar, because when we are picking up the bars, so instead of taking a higher diameter, if you need say 20 mm diameter 4 bars, if you put 4 bars at the corner, if this distance is 650 millimeter for example, then what we do is, instead of providing 4 20 mm bars, we are going to go ahead and provide say 6 16 mm bars. Okay. So in such cases what we do, so we are going to put 2 bars here. So in this case what happens to the center to center distance? This is going to be 325 millimeter. Still it is more than 300 millimeter. So in this case what we do is, again we are going to go for smaller diameter bars, or we put some additional bars, okay, such that the spacing between 2 successive bars in the periphery does not exceed 300 millimeter. This not greater than 300 millimeter. Okay. So you have to adjust and you have to put the reinforcement like that. Okay. So and with that, the next point is transverse reinforcement. Transverse reinforcement 26.5.3.2c. So that is again page 49. Page 49. So pitch. So that is the spacing of the transverse reinforcement. Again, if I take a column like this, rectangular one, so if I look at the plan, I see like this. Okay. So this is the transfer reinforcement, and if I look this in the elevation, I am going to see this. Okay. And if this is the longitudinal reinforcement or the main reinforcement or vertical reinforcement, it is one and the same. Then we are going to put these lateral ties at certain spacing. Okay, lateral ties or lateral reinforcement. So the distance between two successive lateral ties is called the pitch. Okay, spacing or the pitch. So what the code says is, regarding the pitch shall not be more than more than the least of the following. Least of the following. What is that? The least lateral dimension of the compression member next 16 times the diameter, the smallest diameter of the bar, and in no case it should exceed 300 millimeter. I am going to explain what is this. Okay. Next comes, so after the pitch it is the diameter. What is the diameter of the lateral ties we need to choose? One is the diameter of the lateral ties shall not be less than say 1/4 the dia of the largest longitudinal bar and 6 mm. So please write down this, I am going to explain. Is this over? Okay. So let us go point by point. So this is given in the code. If you go to 26.5.3.2c, page 49, you get these points. Okay. So what it means, as I explained before, this is the pitch. That is the vertical distance between two successive lateral ties. So the pitch shall not be more than the least of the following. So it says the least lateral dimension of the compression member. So if I take this rectangular section, so this is the width B and this is the depth, overall depth. D is greater than B. Say for example B is 250 mm. Say D equal to 500 millimeter. So out of these two, this is the smaller one. So this is the least lateral dimension of the column. Is it clear to you? So the code says the least lateral dimension of the compression member, that is, say in this case, say 250 mm. Okay. Next one is 16 times the smallest diameter of the bar. See here, these are longitudinal bars. Say for example, I take these four corner bars as 20 mm dia bars. Okay. And the design requires area of the bars such that we are going to provide 4 20 mm diameter bars at the corners and two 16 millimeter dia bars. So this is 420 mm at the corners. So if you come to the point, second point, 16 times the smallest diameter of the bar. So what is the smallest diameter? Of course, we can have 20, some bars, 2 of 16, okay, then another 2 of 25, like that. We can have different combinations. So in this case, we have 4 of 20 mm diameter, that is the highest size of the bar, and this is 2 of 16, that is 16 mm diameter is the smallest size of the bar. So if you go according to this second point, 16 times the smallest diameter of the bar, 16 times the smallest diameter. What is the smallest diameter? 16 millimeter. 16, that is equal to 256 millimeter. Okay. Next, and in no case it should exceed 300 millimeter. So what it means is, the pitch or the spacing of lateral ties should not exceed these three values. That is, it should not exceed 250 mm, 256 and 300 mm. That means take least of these three values, which is 250 millimeter. Is it clear to you? So what is the maximum spacing? 250 millimeter is the maximum spacing. Take the least value, excuse me, take the least value, and that is going to be the maximum spacing. So we can provide a 250 mm. If you want, you can reduce the spacing below 250 mm. Okay? But you cannot go beyond 250 mm spacing. Then, coming to the diameter of the lateral ties. So the diameter of the lateral ties shall not be less than 1/4 of the diameter of the largest bar and 6 mm. So what it means? 1/4 the diameter of the largest bar. If I take this section, we have 4 of 20 mm, 2 of 16 mm. So 20 millimeter diameter is the largest bar. So 1/4 of the 20 mm is 1/4 of 20 mm, that is equal to 5 mm, and in no case the diameter should be less than 6 mm. That means take higher of these two values. Here least of the three values, in this case higher of these two values. So we are going to go ahead with 6 millimeter diameter bars, okay, and we are going to make lateral ties out of it. Okay. So what in case if this is say 25 mm diameter bars instead of 20, 25 mm, then 1/4 of 25 mm is 6.25 millimeter. So we have two values, one is 6 and the other is 6.25. Take higher of these two values. Okay, so what is the minimum diameter of the lateral ties? That is 6.25 mm. Of course, we don't have bars of 6.25 millimeter diameter. Instead, we are going to go and provide the next higher value, which is 8 millimeter diameter lateral ties. Okay. So these are lateral ties. I have explained this already. I am writing once again, lateral ties. Okay. So I hope this is clear to you. So any doubt, guys? So if you have any doubt, you can ask me anytime. Even you can stop me when this video is running, or else you can contact me separately later to get your doubts clarified. Okay? Thank you.